All right, so this is day 6 of Unit 1. We're looking a lot more in depth at slope, which is our rate of change of linear functions or linear equations. So in geometry, we're not going to worry too much about functions. It's going to be more about just equations. They're really kind of sort of the same thing. But anyway, so here's our EQs. So we're going to define slope a lot more in depth. We're going to learn about point slope form, and we're going to learn about what we're going to use it for. Okay, and then we're going to learn about our Cartesian definition of perpendicular lines, right? So what is slope? So here we've got a goofy little scenario. Okay, so if Cholo Charlie drives his lowrider a cool 25 miles per hour, no matter the speed limit, we've got some questions to answer now. One, what is his velocity? Okay, so velocity is the rate of change in position with respect to time, right? So we can easily figure that out using a graph. Okay, so basically, let's think and I don't think I gave myself the correct graph here. I may have to renumber this because this is only just using ones. Why did I not change it? Anyway, so let's say 25 miles per hour is his velocity, right? So 25 mph, or another way to say that is 25 miles, right, every 1 hour. That's his displacement every 1 hour, so that's his velocity. Okay, so a linear equation in slope-intercept form that would represent this would simply be y, or his velocity, right? His velocity depends on time, so velocity is the dependent variable. So velocity is equal to 25 miles for every hour, right? 25 miles per hour. So our time is our independent variable, the number of hours. Okay, so I didn't even put a graph on here. I didn't even put a question for me to graph it, so I don't know why I put this on here. I think that was just a goof. But what this would look like, right? So let's say miles per hour. Let's start it a little bit different. So I think this is more how far he would go, right? So in 1 hour, he would go 25 miles. In 2 hours, he would go 50 miles, and so on. 75 in 3 hours, right? So if I change the numbering on here, it makes a little more sense. Okay. Anyway, how far will he travel in 4 hours? Well, if we just continue in 4 hours, right, he should go, so 1, 2, 3, and 4, he will go 100 miles. Okay, and it just follows this clear-cut path here. We have a constant rate of change. He's constantly, it says right here, no matter what the speed limit is, he's always going 25 miles per hour. Okay, so that means in 4 hours, he'll only have gone 100 miles. Okay, in 8 hours, well, you could do two things. You could continue to count, or you could just be smart. What's 25 times 8? Or you could just double the 100 miles that he went in half the time. Either way, you arrive at 200 miles. Okay, so pretty straightforward there, right? So here we have another problem involving velocity, right? And in this example, we've got professional Silverado driver Edgar is at the racetrack testing out his new Silverado. I imagine he also has an Edgar haircut. The table below represents his velocity at X seconds. Okay, so what we're looking at now is called acceleration, and acceleration is the change in velocity over the change in time. Okay, so this is what we're really looking at, but that's not really that important. So what is his rate of acceleration, right? So if we look here at his velocity at 2 seconds, right? So 40 miles per hour every 2 seconds. Well, then we've got 80 miles per hour every 4 seconds, right? So what this amounts to is our slope or our rate of change is always equal to delta y over delta x, or change in velocity in this case over the change in time. And we can find that by doing y1 minus y2 over x1 minus x2. We don't really need to do that here, but I just want to illustrate a point. If we just start from here and assume that it's constant, right? His rate of change is very obviously, if we just reduce from what we've got here, 20 miles per hour every 1 second. All I did was reduce, divide by 2, right? That gave me 20 over 1. Okay, so his acceleration is 20 mile per hour increase every second, right? But if I go ahead and use this formula here for slope, okay, I'm going to arrive at the same thing. So if I do 40 minus 80 over 2 minus 4, well, that's going to be negative 40 over negative 2, which of course gives me the same 20 over 1, which is just 20. And that's the same exact rate that I get just from using common sense. Okay, so this is what rate of change is, or slope. Slope is a rate of change. It's a change in your dependent variable with respect to your change in your independent variable, right? So before it was velocity, change in velocity with respect to time. Before that, it was the change in position with respect to time, or the distance traveled with respect to time. Okay, so what that means is time is almost always your independent variable. Not always, almost always. Okay, unless, for the most part, that's what it's going to be. If there's a problem that's a function of time, right, that's going to be your independent variable. Okay, so now let's get into some heavy algebra review. Okay, so, and let me back up here. So what is slope literally? So slope is literally our rate of change. Okay, geometrically speaking, it's our rise over our run, right? So on a graph like this one, right, delta y was 25 miles per hour every 1 hour, right? So that's how we were able to graph it. Okay, so that's geometrically speaking. And algebraically, well, we saw that here on this example. Algebraically is this right here. So slope is given, slope is given as y1 minus y2 over x1 minus x2, which goes back to our geometric definition of our change in y with respect to our change in x. Okay, so forgot to answer that. But now we're on to equation 2, or equation, EQ2. So what is the point slope formula of a linear equation? That is given by y minus y1 is equal to m times x minus x1. This should look familiar from Algebra 1. Okay, so now what can we use this point for? This point slope form for, right? So what we can use it for is to find equations passing through points, right, when we're only given a little bit of information. So for example, right, an equation that passes through the points 3 by negative 6 and has a slope of 2 over 3, right? So when can we use it? Well, we can use point slope now. We have a point, we have a slope, point slope form. Okay, so y minus, so this is x1, y1, y minus y1 is equal to m, this is m, times x minus x1. It's x1 right there. Okay, so all I'm going to do now is just simplify this and get it into the form y equals mx plus b. Okay, but we got to do some quick maths first. So first, I want to take care of this double negative. That becomes a plus 6. Then I'm going to go ahead and distribute. 2/3 times x, 2/3 x, 2/3 times negative 3. Well, this will be a review of what we were doing with point at fractional distance. So I'm going to put the negative 3 over 1, right? And we're going to end up with negative 6 over 3, which of course is just minus 2. Or you can go ahead and say times 3 divided by 3. They're inverses. They cancel. That leaves you with just negative 2. Either way you look at it, you get the same thing. Okay, then we'll subtract 6 from both sides so we can get y by itself and get it into this cube form. And we have y equals 2/3 x minus 8. Okay, example 2. Same idea here. x1, y1. Y minus y1 is equal to m times x minus x1. Okay, and we've got a double negative here, so we're going to call that a plus 6. Okay, so I'm going to distribute. So I'm going to have negative half x minus 3, right? Negative 1/2 times 6, so I'll come over here and write it. So negative 1/2 times 6 over 1. 6 over 2 is just going to be 3, and then we're doing negative times positive, so negative 3. Okay, so that's where I get the minus 3. And then we just add 1 to both sides, and we're left with y equals m x plus b. Okay, next one down. Okay, so here we have another example. Okay, so we're passing through the point negative 9 by negative 1, and we have a slope of 4/3, right? So again, x1, y1, y minus y1. So we know that's going to be a double negative. I'm going to go ahead and write it that way. Is equal to m times x minus x1. So x is negative 9. That's a double negative again. Go ahead and fix that. Okay, so I'm going to distribute. So 4/3 x plus, so that's going to be 12. Okay, and again, I'll work it out over here on the side. 4/3 times 9/1. Okay, 9/3 is simply 3, so we're left with 4 times 3, which of course is where I got the 12 from. Okay? Then we're going to subtract 1 from both sides, and we're left with y equals m x plus b. Okay, so all we were going to do after that is going to go ahead and graph them. Okay, and the way we're going to have to do that, and I could have sworn I had a slide for this. The way we're going to have to do that is, let me pull that up for us here. So I should have a blank graph we can use. Okay, I like how it's just tiny. So let's graph our first one. Okay, so our first one is here in pink, so y equals 2/3 x minus 8. So we're going to graph this one here first. So y equals 2/3 x minus 8. Okay, so our y-intercept is negative 8. Okay, and our m is 2/3. Okay, we can also say our m is negative 2 over negative 3. Positive, or negative divided by negative is still a positive. Okay, so that's going to be important here in a second. And not in this example because I don't have very much room, but in later examples, right? So we're going to count. So our change in y is positive 2. Our change in x is positive 3. So that's where our next point is going to be. So plus 2 plus 3, plus 2 plus 3, and you get the idea. And our graph ends up just looking something like this. So plus 2 plus 3. Give myself a couple more points here just so I can really illustrate this. So this is y equals 2/3 x minus 8. Okay, so let's do another. Let's do another example from our previous little problems. Okay, so I'm going to go ahead and do the one in green now. Okay, so y equals negative half x minus 2. So y equals negative half x. That's no good. Let's see, let's change that setting here. So y equals negative 1/2 x minus 2. So that means my y-intercept is here at negative 2, and my slope is equal to negative 1 over 2 or 1 over negative 2. Okay, and again, now we're going to be able to see why it's important, right? So that means minus 1 plus 2, minus 1 plus 2, minus 1 plus 2. And you get the idea. It's just going to continue. Okay, now what about coming back this other way, right? Well, that's where we're going to use this one. So plus 1 minus 2, plus 1 minus 2, plus 1 minus 2, and you get the idea. Okay, so here we clearly see how that's going to work out. So let me try and, is that a goofy angle for someone that's right-handed? And I know you guys that are left-handed are probably like, yeah, now you know how it feels. Well, only slightly. Only slightly. Okay, so this green line represents y equals negative 1, negative 1 half x minus 2. Let me erase some of this mess. Okay, so all that into perspective, right? We now see a little bit how this is going to work. Okay, and we'll get a lot more practice in class, trust me. Okay, so now what if we have only 2 points? Well, we're still going to use okay, so that's why there's a second thing, right? So the first thing is when we have only a point and a slope, right? So for the second thing is when we only have 2 points. And the reason we're able to do that is because slope can be calculated with just 2 points, assuming this is linear, right? And that's because our change in y over our change in x is the same thing as y1 minus y2 over x1 minus x2. So our change in y over our change in x. So if this is x1, y1, x2, y2, right? We can calculate the equation passing through these 2 points, but first we need to calculate the slope, then we can use point slope. Okay, so to calculate the slope, y1 minus y2 over x1 minus x2. Okay, so 6 minus 3 is negative 3 over negative 5 minus 0, that would just be negative 5. So negative 3 over 5 over negative 5. That's a negative over a negative, so we can just say our slope is equal to 3 over 5. Then from here, it's just plugging into point slope. So y minus y1, which is 6, is equal to m times x minus x1, which is negative 5. So we're going to say plus 5 because it would double negative. Then we distribute. Okay, that's going to give me 3/5 x plus 3. Okay, then we're going to add 6 to both sides. So y is equal to mx plus b after we add 6 to both sides. And now we have y equals mx plus b. So pretty straightforward stuff here. Okay, so again, let's label x1, y1, x2, y2. We need to calculate m first to see what equation passes through these 2 points, right? And so let me back up here. Let me back up. So let's look back at example 1 here, right? And I did this in red. Okay, so we would see that our equation passes through the point 3 by negative 6. Let's see if that's true. So 3 by negative 6. Holy dog crap, it's true. There it is. 3 by negative 6. And then the guy in green here, right, should pass through the point negative 6 by positive 1. So negative 6 by positive 1, here it is right there, all ugly drawn, but negative 6 by positive 1. Okay, so we're going to see that this equation, and I'm still using green, we're going to see that this equation and the one after this are going to pass through both of these points if I graph them. Okay, and just for the sake of time on this video, I'm probably not going to do that, but just so you know. Okay, so m is equal to y1 minus y2 over x1 minus x2. So 14 minus 2 is 12 over negative 6 equals negative 2. So then we're just going to plug in a point slope. Y minus y1 is equal to m times x minus x1. So that's going to be plus because it'd be a double negative. Okay, distribute. Add 14 to both sides, and we get y equals negative 2x plus 12. And that would be our final answer there. Okay, last example. x1, y1, x2, y2. Okay, and I'll probably show you this example on a graph, maybe. I don't know. Now, I'll probably show you this example 1 here on the graph before I end the video. Wait, I still have one more slide. Yeah, no, never mind. Okay, so m, let's calculate m. So that's 0 minus 1 over 5 minus 15, negative 1 over negative 10. That's going to be 1 over 10 is our slope. So y minus y1 equals m times x minus x1. And I'm having a brain fart. Why am I having a brain fart? That's 5. What's the matter with me? Okay, so distribute. Okay, so this would be minus 1/2. Okay, and let's show y. So 1 over 10 times negative 5 over 1. That would be negative 5 over 10, reduces down to negative 1/2. Okay, 5 and 10 are both reducible by a factor of 5. Okay, that's where I get negative 1/2 from. And y minus nothing, well, that's just y. So we're already done. Yay, hooray. Okay, so last thing I want us to talk about, and you'll see this in class. Okay, if two equations are perpendicular, then their slopes will be reciprocals and have opposite signs. And I could have sworn that I put a Desmos link onto here, but I guess I left that out because I'm stupid. Okay, so let's see if that's true or false, right? So the two equations will be perpendicular if the slopes are opposite signs and reciprocal, right? So let's do something like y equals 3x plus 2, and y equals, well, opposite signs, so negative. And then what is the reciprocal of 3? Well, 3 as a fraction is 3 over 1, so if we flip that over, that's just 1 over 3. And of course, we put the x here, and then intercept doesn't matter. We'll just say, okay, maybe not that far. We'll just say that. Okay, and we can see right here, I mean, that is a 90-degree angle. Okay, 100%. And you will easily be able to see that if you physically graph this out yourself on graph paper or on a graphing board. So this is absolutely, this is absolutely true. And to answer EQ4, okay, well, I'll tell you what. To answer EQ4, let's not even write one out because we already have one written out for us. This conjecture right here is already proven true, and it's true in the converse as well. If their slopes are reciprocals and have opposite signs, then the two equations are perpendicular. So this is literally a definition for, in the Cartesian sense, for perpendicular lines. And I say Cartesian because we're talking about the Cartesian coordinate plane. Okay, so anyway, that's all I got for this video. Any questions, obviously, let me know. Otherwise, goodbye.